Hello and welcome everyone. In this day 41 learning, we are going to be looking at algorithm classification. We have covered many different algorithms and data structures. Now it's time for us to understand. Uh, uh, let's say if we are given a problem, what is the best way to approach, or what is the best way to solve a given problem, right? So for that to know, we have different implementation styles. So we can classify this based on implementation styles and design and behavior, and lastly type of problem. Okay, so these are few different broad ways that we can classify. Um when we are talking about implementation, you can think about implementation like an series approach where we write a bunch of statements in series, iterative, recursive, or parallel and distributed. In case of design, we have things like brute force. Just to solve a problem, we can have a direct solution. Brute force, divide, conquer, divide and conquer, divide and conquer, greedy, dynamic programming, dynamic programming, dynamic programming, and backtracking. Backtracking, right? So these are few possibilities in uh, solution design of a problem. In case of behavior, so let's say we want the exact output or approximate estimate output, or randomized randomized or deterministic, right? So these are few types. So, and types of problems might be either we get a searching type problem, searching, sorting, graph type problems, graph trees, strings, or so on. So there can be different problems of this type, right? So these are different classifications that we can come about. Implementation, let's talk about each. Let's go with first one, the implementation style. We will not talk about all of these items like series, iterative, and recursive, but let's understand how they look like, at least just for us to recall things, right? So first one is implementation style. Okay, so First one is a series algorithm. Let's say algorithm. So let's say we are required to compute a tax, right? So the way that we can do is, let's say we have our price and tax rate. So in a series algorithm, given these two values parameters, we can compute total price is equals to price plus tax. So tax calculation can be equal to price into tax rate divided by 100. And then we can add this component here, price plus tax, right? So that would give the total price that the customer has to pay. So that can be a simple example where series algorithm is there. So we just follow a series of steps without much of a complexity, right? So iterative algorithm, in case of iterative algorithm, uh, let's say we are required to uh, iterate through an array or sum an array of numbers. Let's say we are given with 10, 18, 6, 3, 72 or something like this. So we are required to calculate sum of array of numbers. So we can use for loops, while, or do while or any iterative or so on, right? So we write a for loop, we iterate through each number and sum it with a result value or a sum variable, and then we keep adding it to the sum variable and finally we return it, right? So that's an example of simple iterative algorithm. Okay, so third one is recursive approach. So let's say we are given to find a factorial of a problem, right? So the way that we approach is factorial of 5 is n into n minus 1 factorial. So this can be a recursive approach where f of n at 0, which is equals to f of 0, is equals to 1, and at 1, f of 1 is equals to 1. These are the few base conditions. With these, a recursive function can be implemented and any number can be calculated with a factorial of n, right? So that's a recursive uh, approach. So next would be with respect to parallel implementation. Let's say we are so let's say we are given few set of uh, activities. So let's say in Java we have threads which can help us in performing multiple activities parallel. So let's say we want to compute a certain activity parallelly, so we can allocate a single thread to each activity, and the other threads can take up different kind of activities, and they can all work in parallel and return faster output, right? So that's a simple example, but yeah, there are practical examples to that. So one example that I had at least come across is with respect to uh, a web scraper which can run parallelly across multiple pages, right? So there can be many other examples that uh, many others would have come across. Please to post your experience with parallel implementation in the comments, right? So next we have a similar kind of idea with this distributed implementation. So today with advancement in cloud computing, so we don't need to have our systems up all the time. So we can utilize a cloud machine on some AWS EC2 instance or so and spin up a server really quick and have it run for certain period of time and another server run at a certain period of time, and we can also configure it to run at different locations and many different things with uh, the rate slabs and such things, right, to for optimal usage. So yeah, that's about distributed computing, which involves usage of multiple servers or computers. So cloud helps us do that better, right? So yeah, that was a few different things in the implementation style. Next, let's look at design, right? Design of an algorithm. Let me start this off in a new page. So we are going to be looking at first one, which is brute force approach. So in case of design style of algorithms, so first one is brute force. So let's say we want to find sum of two numbers in a large array, an array of numbers. Let's say 3, 7, 8, 11, and 5 and 6. So let's say we want to, let me change this to 4. So let's say we want to find a sum which yields us to sum of two numbers is equals to 10 in array. So we need to find these two numbers. So the way that we do it in brute force is take each number and add them, try adding them across all the other numbers and see if something is possible. Else we move to this number and we do the same, trying to add it with the rest of the numbers, including this one. So if it doesn't lead to a number, then we return false. Else we find those two numbers and return them. So for example, 4 and 6 leads to uh, 4 and 6 leads to 10, right? So this is brute force approach, right? So there is code implementation for it, but yeah, I will leave it at that point. There are many other brute force techniques that one can imagine about. You can write your thoughts or examples about brute force problems in the comment section, right? So divide and conquer. So we have seen many searching and sorting algorithms. So divide and conquer, for example, we have a binary search where we find the midpoint. Let's say we are required to find a value. So we firstly look at the mid portion of the array and then we compare it to the search number. If the search number is less than the mid value, then we move the mid value to the leftmost side and again recalculate the mid to the leftmost side, and the right pointer is switched to middle pointer and then left pointer stays at the initial pointer, and then we calculate the binary search again. So there are other examples like merge sort, binary search, merge sort, merge, quick, quick sort, so on, right? So divide and conquer has many different examples that we have looked at. So yeah, third one is greedy algorithms. So let's say greedy algorithm. Let's say we want to. Let's say we have a tree of items. Let's say we are here and we are required to find the maximum value. Let's say we get 5, 10, and 2, and this one has a jackpot of 100, and 3, and in case of 10 it has 1 and 5. So let's say these are the values. Let's say if someone asks us to find what is the path which leads us to the maximum weight, right? So let's say if we are choosing greedy algorithm, so the first option that we ask is what is the highest value of a node in the first layer. So 10 is the one that we choose. So from 10 we explore what is the next highest value. So 10 plus 5, that would be 15 in greedy algorithm. But actually if you see, the lowest value here is 2, and this has a value of 300, which is leading to 3, not 2 in this path, right? While this one led to 15, so which is not a right value. So greedy algorithm definitely doesn't give a uh, right solution at every time, but yeah, that's an approach that is there. But yeah, so there are examples such as Dijkstra's, but it leads to a solution. No doubt, it leads to a solution. Sometimes there might be weighted edges that can be much better or an optimized route, right? So let's say in pathfinding algorithm, we have come across Dijkstra's algorithm, Dijkstra's and Prim's algorithm. So they are common examples of greedy algorithms, right? So next is dynamic programming, which we have not looked at. Maybe we will spend some time on it. Even the greedy algorithm, maybe we will uh, spend some time on it in the next session, right? So next we will talk about dynamic programming. Even though we have not looked at it, let's understand what dynamic programming means. So let's say we are having to find a Fibonacci of number f of 5. We know that f of 5 can also occur if we are calculating f of 6, because 6 into f of 5, 6 minus 1, this is, so it is important for us to have this value cached out, and then the other set of values also cached out, so that the repeated set of activities can be used with a cache kind of a memory storage, right? So for example, we can have a memory array of n, and we can say f of uh, 0 is 1, f of 1 is 1, f of 2 is 1, f of 3 is, f of 2 is 2, f of 3 is 3 into 2, which is 6, f of 4 is 4 into 24, f of 5, which can be 120, something like this, right? So we can simply cache out all these values, and we can use these previous values to calculate the next one. So that's the whole idea with dynamic programming. Next and last one, or the second last one, is backtracking, right? So what happens in backtracking is, let's say we are required to generate a binary string. What we do is, let's say we start off with 0 and 1, then we start generating patterns such as 0, 1, 1, or 0, 0, 0, 0, 1. So this can be 0, 0, 0, 0, 0, 1. Same can go here, 0, 1, 0, 0, 1, 1, something like this. So these can be a possible pattern. So 0, 1, or 1, 0, and 1, 1. This can have 1, 0, 0. This can have 1, 1, 1, and 1, 0, 1, 1, 1, 0, something like this, right? So yeah, so consider it this way. So we can have common examples with backtracking, like generation of a binary number. So as you can see here, we have bunch of 3-digit binary strings generated here from a empty string, let's say. So, and let's say if we are asked to find a value of 0, 1, 1, then we can say that this is an optimal path, right? If this doesn't lead, then we can uh, either backtrack it, and then we can come back here and generate it. So backtracking is like trying all possible options. So yeah, so it can also help in search for a word. So here we had 0 and 1. There can be 26 characters, and there can be 26 different options, and there can be backtracking done on that. So yeah, that's another example as well. So the last, there is last one other topic that we had here. So it's about branch and bound. So it is a similar kind of topic, but it is an optimized approach with backtracking with slightly an optimization where a branch is explored completely, and then if it gives a good answer, then we, if it is leading to a proper output, like for example, we, if we want to find 0, 1, 1, then we head to this branch, and we check if the characters are matching to the final output that we are looking for, and slowly we iterate to these two branches as well, and finally lead here. So, and we avoid entirety of this piece of execution. So that's a slightly more optimized technique with branches and bound technique, right? So these are few approaches that we had in design implementation, right? So yeah, so yeah, like we said, we looked at implementation techniques, design techniques, and behavior. So sometimes a problem might ask for an exact solution. Sometimes, let's say we are calculating tax, so we might need exact number, and sometimes we might need an appropriate number. So there can be different techniques, and a randomized number. Let's say we might have slabbings for them. So there can be different approaches or behaviors that a problem can be expecting, and we, let's say we read a problem statement, we also might understand if it's of a, if it involves searching, sorting, or graph type problems, which also involves a combination of searching, sorting, or a string kind of a problems, which involves these other uh, types as well. So yeah, these are few classifications that we can broadly think about when we come across different problems, right? So yeah, as we solve more problems, we can get an intuition or a feel for it. There is always no right or wrong answers. It's just about trying out what's the best possibility, and there can be a better approach tomorrow. Another new algorithm might come into the picture, right? It's just about solving more problems and getting to learn things, right? I will stop this video for now. Hope you found this video helpful. Please do like and subscribe to my channel. Please do post comments about any of the topics that we had so far, and let me see if I can address them in the upcoming sessions. Right? Hope you found this video helpful. Please do like and subscribe to my channel. Thank you.